Our next talk will be by Luiz and Battisti. It's about V-PRISM, a net-based architecture to virtualize multimedia sensors in the Internet of Things.
Hi everyone, it's a pleasure to be here today, and we are talking about our working products, whose name is V-PRISM, an net-based architecture to virtualize multimedia sensors in the Internet of Things. My name is Anselmo, and my advisor is Professor Web, and my co-advisor is we are talking about our context and motivation, our goals, talk about our architecture, whose name is V-PRISM, about our proof of concept and experiments, and our final results. First, in the Internet of Things, the device becomes a control source of data, and this data was consumed through one application. Usually the application and the sensor, they are not the same network and don't have the same protocols. And to deliver data from sensor to application, usually we have a middle layer that do this work. And when we use cloud as this middle layer, the name of it is Cloud of Things. Usually Cloud of Things is mainly based on virtualization. And we have a virtual entity that abstracts the physical determinant of the sensors. A subset of IoT is IoMT, Internet of Multimedia Things. And we're talking about only camera and microphone. Usually, multimedia applications are latency sensitive, and if we use cloud as this middle layer, sometimes not a good idea because we can predict the latency in this scenario. So, one strategy to solve this problem is bring the computation and storage as near as possible to the source of data. Edge computing is a good start point because it usually is near from the physical device that produces the data. So we are proposing an architecture to create and manage virtual multimedia sensors in the edge. The main components of the architecture is deploy and run in the edge. So we have in the left the physical devices, and this device produces multimedia stream that are received in our architecture, processing and delivering the multimedia stream to application that is deployed in the cloud or even in the edge. And our hypotheses are a single device can be used to as a source of data for multiple different types of virtual multimedia sensors. And the use of our architecture, we can reduce them simply using M-Bed consumption in the edge device, and it's a problem because in the edge device usually we have no power and no CPU. And using V-PRISM, we can reduce the bandwidth consumption in the edge network. And here we have a camera who's in the stream is sending for two different applications, and each one wants to receive the multimedia stream in different formats. The first one only wants to receive the audio, the second one only wants to receive grayscale video, and the third one wants to receive only information that, for example, motion detection processed by camera. Here we have overview about our architecture. On the bottom we have the physical devices, and here we are talking about, for example, USB camera, Bluetooth microphone, RTSP device, and the data was produced here, and it ingress in our architecture for a component called source. The source is like a driver that knows how to connect with each different type of source. If we have a Bluetooth microphone, we will have a source that knows how to talk with the Bluetooth microphone. And if we have a USB camera, we will have a source that knows how to talk with this USB camera. The source sends data through one or more VMS, and here is where our main process occurs. The VMS receives data from a source, or it receives data from another VMS, and we can change the process in to produce more complex results to application. We can have VMS for all kind of things. For example, plot a video, or conversion to a grayscale, or motion detection, or noise detection. We can produce here. And the source and the VMS, they are not the same process, and through send control data, we are using a function subscriber strategy. The applications will receive data directly from the VMS, and the applications request they start with new VMS using IoT broker, and the messages from IoT broker are processed here in this component whose name is Maestro, and we orchestrate the start to stop by the source and VMS. They know how to do everything here inside our application. And to test this architecture, we develop proof of concept, and here you have an overview about it. Our virtual nodes, in this case our VMS and the source, they are Docker containers running inside the process that are our VMS and our source. We can develop the VMS and source in whatever programming language we want. You only need to Dockerize this application to run inside a Docker container. We develop a client that we use to start the VMS and the source using Node.js API. Here we have a view about our web clients. We have developed 5 different VMS types, and you can start as many VMS you want using these types. We have grayscale video. We receive color video and convert to grayscale. We have crop video that receives a video and the video classification only a fraction of its video. UDP to UDP, a noise detector, and a video merge. Here we have, we are starting a new VMS. In this case, is a noise detector, and each type of VMS receives different parameters when we start it. In this case, this VMS receives 4 parameters. The first one is defined what is the noise limit when we trigger to MQTT server a message, and the MQTT server is starting this IP and in this port. And here we have the VMS running. We have a noise, the name of our VMS. Here we have the parameters we use to start the application, and this VMS is binded with this source. We can have many different VMS binded with the same physical device, and it's improve a lot the return over investment if you use this strategy, because you can deploy only a single camera and use it in many different applications. Here we have the message in MQTT server. The noise was higher than 0.02, and here is the message. And here we have the view of the containers that was started. We have here the VMS that runs the noise detector, and here the container that runs the MIG device. And we can start as many VMS as we want. Here we have example of application. We have a single camera that sends data for 2 different applications. At one FP2. The FP2 receives the data, only part of a fraction of this data, and in grayscale mode. And the second one receives only a fraction of this view. We can use only one camera and send data to different applications. Here we have another example. We have 2 different cameras, and the data of this camera was sent to one single VMS that merged the stream and delivered to an application. And the application received only one stream with the result of 2 different devices. This shows that we can improve the return over the investment for the infrastructure providers. And to test the idea about the reduce of battery CPU and energy consumption, we developed an experiment, 2 different experiments. The first one here, we have 20 apps that ask to a single device for video. The device is a cell phone that runs RTSP server, and the device sends to application the video. And in the second scenario, we are using our approach, and here the 20 apps, and the apps are video viewer, and they are receiving the media stream using the VMS and not collecting data directly from the device. And here we have the results. We run the experiment, each experiment for 5 minutes, and here we have the means of it. Data was collected in the device, and we use the battery stats software. It's a software developed by Android team. And our approach is the blue one, and the red one is the naive approach. You can see when the number of applications grow, when we consume data directly from the device, the amount of resource increase a lot. And when we use our approach, the amount of resource stay more or less stable. And here we have, in this case, the network here is the IoT network. And here we have the CPU usage. Again, when we use our strategy, the use is more or less the same, and we consume data directly from the device, the amount of CPU usage increase a lot. We test battery 2, and the results are more or less the same. Using our approach, the results stay more or less stable. Well, we propose an architecture to create and manage virtual multimedia sensors, and the adoption of the architecture can reduce the CPU usage in the device, the battery consumption, and the IoT network bandwidth. And using this strategy, we show that we can deliver to many different applications, different types of multimedia stream produced by only one physical device. And we can use, for example, a $5 camera serving applications that are far more complex than the IoT device can produce. Here this is a working in project work, and here we are developing more complex VMS like facial recognition and speech detection in the edge. We are making tests using Raspberry Pi, and here we have our code. They are deployed on GitHub. You can access, download, and run in your machine. It's called Dockerize. It's more or less easy to run it. We have a step-by-step. and we have a quick video. Okay, here we are starting our containers, and after that we are access the web client. Here we have our physical devices, and we are starting the service with a video sample and with a webcam. After that, we are starting our VMS type. Each VMS type will pass the parameters. In this case, we are sending data to this IP and port. The application is running here. We are creating two different VMS. One is a grayscale, and the other one is a video merge. And we are sending data for this IP and port. And here we will bind the VMS with service. We are binding the webcam with the grayscale VMS, and we are binding now the video merge with the two services, webcam and the video ball. And now we are simulating the applications. Here we are starting the application in the machine with that IP and port, two different applications, and the result will be shown now. And here we have the webcam in grayscale, and here we have the result of VMS video mesh, the webcam and the video ball in the same script application. Thanks for watching. Okay. No questions?
Questions?
Anselmo, very nice presentation. Congratulations on your work. I have a few questions about the experiments. I don't think they really show the whole potential of V-PRISM like you proposed, because the experiment was actually very naive and it's showing expected results, right? So if you have any IoT broker with an MQTT and you would have the same results as you got, like with only one stream being sent from the IoT device to the broker, and then with a publish-subscribe solution, it would feed all the others. But what I think is the potential that you have is to have the multiple different types of contents and features, like processing of the video, cropping, making it different things. But what was shown there, it looked to me like a regular publish-subscribe solution with an IoT broker. No, they were saying no. So maybe there's some difference that I didn't get, right? But it looks like a regular IoT broker where the device sends only one stream, and the broker is sending these streams to all the applications that subscribe to it. But my point is, I'm actually interested in another question. When you finished about the facial recognition, it was not clear to me if your VMS, you can have different edge devices talking to each other to do something like tracking of users. So if you have an application that is trying to do facial recognition, and if you identify a terrorist in one of the places, one of the cameras, and if that information could be sent to different edges, so that would activate the camera and track a given user.
Okay. This test we perform, the idea behind any book and subscriber, it's not the multimedia stream, it's only the control data. And the multimedia stream is not passing through the book and subscriber. And each VMS is running inside the Docker container. And we choose this approach because we can move it and deploy it in different edge devices. And it permits that we can improve. For example, if we need more power computation, we can migrate this Docker container to a better machine. And the idea is to develop an architecture that could be improved by create new types of VMS. And the idea of track differences is one possible VMS type that could be developed.
So okay, so it is possible to communicate between one edge to another edge.
Yes. The each VMS here. Each VMS is running inside Docker, and we can deploy it in different edge nodes. Don't need to stay in only one single node. For example, we can have the VMS 2 in one edge and VMS 1 in another edge.
Thank you.
More questions?
Thanks, Anselmo, for your presentation. Now, I have one specific question about latency constraints, because I've seen you show some results about bandwidth, CPU, and memory, but on your experiment result, it was possible to see there was like some latency happening between the video streams, between the different applications. So, could you talk about a little bit of which would be like the latency constraints?
It's because it's a work in progress. We are discussing how we will measure this type of thing. We already have a naive approach, and we are improving it. It's because of that we don't have a graph about latency, but we are trying hard in this way.
More questions? I have a final one, much more curiosity. Is there any real application that you could show it for us as an example of how this could be fully used? I really hope that I imagine some usages for the system, but I'm not sure if they are exactly what you meant. So could you give us an answer?
Okay, for example, here in we have some cameras in our university, and it's difficult to collect data from this device and deliver to different applications. It's not so easy. When we saw, for example, in a television show, the video of a webcam, usually a cell phone that records a screen of this, because it's difficult to get this data. And this architecture we are developing to solve this problem. We can use the physical device that already is deployed in the field, and the data can be delivered to different applications. And we can develop, for example, we have some strange ideas. For example, I live near the spark, I don't know how to call spark in English, and boats. And I think in a lot of VMS that trigger when the boat is near. So whatever you can imagine in a video, you can create a VMS, for example. You can face recognition, motion detection. We develop a noise detector. We can deploy, for example, I have a room, and if some noise happened during the midnight, call the police. We can have we can develop. It's difficult to do it without an architect, because each different type of device have different types of communication. And we are trying to make it's easier.
Okay. Thank you.